The Materials World modules are hands-on, inquiry and design-based curriculum units for middle and high school students. Using principles from the interdisciplinary fields of materials science and nanotechnology, this curriculum aligns well with STEM objectives, engages students, and adds relevance to existing curriculum.
Hello, my name is Tom Young. I'm a science teacher at Waukesha South High School. And I'm here to tell you a little bit about the ceramics module from Material World's modules at Northwestern University. You know, everything has to be made out of something. And for many of the things in our students' lives, that something is a ceramic material. Now, most of us think about ceramics, cups, saucers, plates, these types of things, or maybe artwork, statuary, or the bathroom, toilets, sinks. But ceramics is so much more in our environment. They fill our everyday lives in places we know and places we don't know. Like, do you know the inside of every electronic device has ceramics? Every integrated circuit is built on a ceramic material. So that means computers, cell phones, CD players, Game Boys, just about anything you have is going to have a ceramic material inside. Space shuttle tiles. Now, most of us don't get a chance to see the space shuttle in person, but it's still there. It's making advances in science, and the tiles that are used are there for heat absorption on re-entry. They're very, very lightweight, but yet they absorb tremendous amounts of heat energy. Closer to home, simple glass is a ceramic material. Whether it's a glass that you use for drinking or for jars, it's still the same. Concrete is technically another type of ceramic material. Concrete in roadways and sidewalks. High tech, you can get ceramics that are different than just the chips, but they're still ceramic materials. And even as simple as the artwork held up on your refrigerator at home is made out of a ceramic type of magnet. So you can see ceramics are all over our students' lives. So it makes sense to put part of that ceramic information into their education. Now, I know what you're saying. I don't have time to put ceramics in. I have trouble getting in what I have to get in now. I understand. I teach in a classroom with the same students that you do, the same time constraints, the same kind of course constraints. And now with national standards being put into all of our educations and standardized testing, true, it's like the crunch is even worse than it was before. So maybe as what you see with the ceramics module, try not to look at it as an addition to your curriculum. Take a look at it as maybe a substitution, a way of teaching some of the things you already do now with different props. Now, the ceramics module is composed of six activities. In the first activity, the students compare the ceramic materials to others, like wood and metal and fiber and plastic, for various properties, thermal properties, electrical properties, strength properties, types of things. After they take a look at the properties of what ceramics are compared to other things, then they go out and take a look. What are made out of ceramic materials? Where are they in their environment? And they come in and talk about what they think are made out of ceramics and what things are not. The activity on porosity. Now, porosity is a term most of us don't use and students don't think about, but porosity is simply holes. When we think of solid materials, then and density, then those solid materials, most things, we think of that's just a solid that doesn't have anything to it as far as on its internal structure. Students see that's a piece of copper or that's a piece of glass. But the density of a material, as we normally teach it, usually involves measuring the macroscopic, the length and the width, and using a formula, and with the mass, and we calculate a number. And the students know that the density of copper is so many grams per cubic centimeter, and then they move on. And they'll know it's more than water or less than steel, that kind of thing. But they really don't understand the concept of density. If we think about two materials that are the same chemical structure, gravel and sand, they're just in different forms. Are the densities of these two samples the same? There's a difference between the density of the material and the density of the object. Now, engineers, of which many of your students are going to be engineers in the future, have to worry about the object as well as the material that it's made out of. So therefore, how do you control the density of the object? How dense is this compared to this one? And it comes down to controlling the holes. And as students work through the exercises, things that they once thought of as solid really don't quite look so solid anymore. And in today's world of new materials, a lot is happening at the nanostructure, at the molecular structure. And that's where the holes and how things fit together really come together. The exercise on slip casting, in which they take a powder, like zinc oxide, and take this powder and turn it into something that's hard and usable as a ceramic material. In order to get from one to the other, the process of slip casting, which still dominates the ceramics industry, has to be used. But how do you turn that powder into something that you can pour into a mold? You could add water. And if we add a little water to this powder, and stir it up, we don't really get too much of a powder at all. We get a sticky substance that's much more like peanut butter. Kind of sticks to the spatula and doesn't pour so well. That's never going to pour into a mold. So, reason is that you have these little particles that are charged. Now, in chemistry, we talk about polar molecules, talk about van der Waals forces, and the electrostatic nature of these things, and the students shake their heads, and we shake our heads, and we kind of move on to the next thing. And they never really understand or get a feel for what these forces. I never got a feel for what these forces were like until I started trying to slip cast this zinc oxide powder. And it clumps up because these molecules are grabbing onto each other and won't let go. They won't slide past each other, they just grab onto each other. So if we add a little bit of a chemical substance that really is nothing different than a polyelectrolyte, something that gives up electrons or takes electrons, we just add in a few drops, that clumpy, sticky mess now becomes very liquid. In fact, it's a lot like milk and just pours. And you can imagine now I've got something that is pourable into a mold. So I took a powder, turned it into a clumpy mess I couldn't work with, and now into a liquid that can be done. Students are amazed by this. They love it. To take something and change its properties just by adding a few little chemicals is like the old magic sets they may have had when they were a kid. And so we need to bring a little bit of that magic back into this situation. Slip casting is an easy process. And simply by pouring that onto a plaster mold, and the mold is simple. If we just take a little piece of copper tubing and pour it in, we get a very small, kind of a dime-shaped, what we call a green body of ceramic material. But it really isn't ceramic properties yet, because it's breaks very easily, it's chalky. It's a lot like an antacid tablet if you've ever seen one of those. And it has many of the same kind of physical properties. But it doesn't have what we think and remember as ceramic properties. It's not hard and brittle. But now by taking that slip cast and by controlling how much we pour on there, how long we let it sit, we can change the properties that it has, how big it is, and what it'll do. The fun comes when they sinter it. Sintering is a kind of a fancy name for baking. Put it in the oven. Unfortunately, you need an oven that's got high temperatures and is controlled very well. And if you sinter it for high enough temperatures and for long enough, it turns into the same white piece that was very soft turns into a much harder and smaller little disc. And if we drop it on here, you can see and hear that this now is much harder with more ceramic-like properties. This little piece also has something besides zinc oxide in it. And that extra something gives it an electrical property that it didn't have before. And this is one of those exciting new applications of ceramics. This is something which, in this case, is called a varistor. A varistor is simply a variable resistor. It has high resistance at one temperature, below a certain voltage, and low resistance above that voltage. It's got kind of a turn-on point. This is the heart of a surge protector. The surge protectors that you have in your homes that are protecting computers and other electronic equipment that are in offices all over the country and all over the world have this type of material as its base. The design project, which finishes this module, is to have the students take the zinc oxide powder and design a way to come up with a varistor that will serve specific voltage and current requirements. Now, it may seem a little challenging at first, and it does to them, but they've gone through all the steps. The porosity discussion, the slip casting, they've fired it in the oven, and so they know how to do it. They just need to be allowed the time and the opportunity to put it together. And when it works, when they see the lights go on or off at the right voltages, they really do get excited. It does take some time because you're dealing with things that are going to work in the oven at high temperatures, and it does take them hours to cook. And it takes a high temperature controlled oven. Now, you can't go to the Family and Consumer Ed because a normal kitchen oven just won't do it. You need high temperatures and control. But you might have an art department that has an art kiln. And just about every art kiln now is computer controlled, and they all have high enough temperatures. But you've never used that art kiln, have you? So that means you have to work with that art teacher, which is not a bad thing. They're nice people. And in my situation, they really liked helping me out. It's like somebody was coming to see them for technical advice. They loved it. And as a spin-off, I now have somehow become the technical advisor for the art department. They come and ask me questions, chemistry questions especially, because students in my chemistry class, having seen us work together, are now working a little bit better at their chemical equations and their reaction chemistry because they're more interested in the technical aspects of glazes. And they want to get that glaze that nobody else has, and they want to be able to read and understand what it is. So there's a two-way street there. The art students are understanding more about the technology of their craft, and science students are seeing applications in the art world and using other applications that they didn't see before. It's becoming a little bit more alive, and we're working together. It does take time. It takes hours for these things to fire, but you don't have to sit there and watch it. You turn on the kiln and it does its thing, and you come back later. But it does take class time preparation. But students love projects. They love to work together with each other. They like to talk to each other. They don't have to listen to somebody talking. They can research on their own. And at the end, there's a tangible result. They get something that they can put in their hands, and they can see the meters move and the lights go on and off, and it works or it doesn't work. In either case, they're still happy with it. So there is a trade-off. I'm willing to give up maybe the old lab that I really like to do. Maybe I won't do as many problem sets as I did before in order to get some of this information to them. We're still teaching the same content that we did before. And in the long run, I think the students benefit because they do solve problems better than they did before. And they do work together and are capable of analyzing what they've done and to go back and make changes if necessary. Thank you very much.